Alright, let's get started with using chords, section 10.3. In this section, we want to use chords of circles to find lengths and arc measures. And our essential question, what are two ways to determine when a chord is a diameter of a circle? So a couple things we need to recall. A chord is a segment with end points on a circle. So any chord is going to divide the circle into two arcs. Here we have two examples. Our first example, the diameter, it's always a chord, and you can see that it splits the circle into two different arcs, which happen to be semicircles. This chord divides the circle into a minor arc and a major arc. All right, so let's get familiar with our first theorem. It's our congruent corresponding chords theorem. In the same circle, or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. For example, we have segment AB, a chord, congruent to chord CD, and we know that by the marks. So that means that our corresponding arcs are congruent. So we can say arc AB is congruent to arc CD. Again, make sure you're learning your implied statements, so it's good to practice writing them. It's good to practice writing them in your notes. So let's take a look at our first example where we want to use congruent chords to find an arc measure. So here we're given circle P is congruent to circle Q. So what that means is that our radii are congruent. And we have two matching double marks for each radii of circle P and circle Q. Then we're told that segment FG, which is a chord, is congruent to segment JK, a chord in the other circle. And then we have our single marks indicating that they're congruent. And then we have that the measure of arc JK, so that's this piece right here from J to K along the circle, has a measure of 80 degrees. So what then is the measure of arc GF? So let's see what we want here. We want this arc measure right along here. Well, based on the theorem we just stated, we know that the measure of arc GF must be equal to 80 degrees. And that's because in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Next, we have a definition of bisecting arcs. So we're already familiar with this word bisecting. It's to cut something into two equal halves. So if we're talking about bisecting arcs, then we're talking about two arcs that are divided into equal parts. So here we have, if arc XY is congruent to arc YZ, then the point Y and any line segment or ray that contains Y bisects arc XYZ. So look at your illustration here to help you understand this definition. So that leads us to our next theorem, our perpendicular chord bisector theorem. If a diameter of a circle is perpendicular to a chord, as you can see here, the diameter GE is perpendicular to chord DF by our right angle symbol. Then the diameter bisects the chord and its arc. So that makes this piece equal to this piece. Therefore, arc GD is congruent to arc GF. And here's our implied statement. Circles of diameter perpendicular to the chord implies diameter bisects chord and its arc. All right, so let's use a diameter in this example that bisects a chord. So we want to find the length of HK. All right, so we know that the length of HK, which is the entire chord, is equal to 2 times the length of NK. And that's because when a diameter intersects a chord, it's perpendicular bisector. So that makes the length of HK twice the length of NK. So we substitute the length of NK with 7, and we want 2 times 7. So the full length of HK is going to be 14. All right, now let's find the measure of arc HK. Now, based on our first theorem, or on our previous theorem, we know that the arcs are going to be congruent. So that makes measure of arc HJ equal to the measure of arc JK. So we can substitute our expressions 11x, which equals 70 plus x. Solve for x, and we get 10x equals 70. So we get that x equals 10. So now we can take that x equals 10 and substitute it in for our expression where we see 70 plus x, which is the measure of arc JK, getting us 77 degrees. So for finding the measure of arc HK, which is all the way around, then we want to double that 77. So the measure of arc HK comes out to be 154 degrees. All right, our next theorem is the perpendicular chord bisector theorem. So if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. If segment QS is a perpendicular bisector of segment TR, then segment QS is a diameter of the circle. So it's almost the switch of the previous theorem. And here's your implied statement, so make sure you're learning that, writing it in your notes to give you practice time. So careful with the wording here, but basically if your diameter bisects the chord, if the diameter is perpendicular to the chord, then it bisects the chord and its arc. So let's take a look at this real-world situation where we have 3 bushes arranged in a garden, as shown. So here's our bushes here, here, and here. Where should you place a sprinkler so that it is the same distance from each bush? Well, let's start by labeling and connecting our bushes. So we have bush A, bush B, bush C, connected by segments, as illustrated here. After you connect, next we want to show the perpendicular bisectors of each of these segments. So you draw the perpendicular bisectors of both AB and BC. And what we notice is that the point where the perpendicular bisectors intersect, that's where we want to place the sprinkler so that it is equidistant from all the bushes. All right, our next theorem is our equidistant chords theorem. So in the same circle or in congruent circles, 2 chords are congruent if they are equidistant from the center. So here we see AB is congruent to CD if and only if EF is equal to EG. I was missing the label for point E, so I just added that. So we have the center E for circle E. So what we're saying is that if 2 chords are congruent, then they have to be equidistant from the center. So that makes this segment equal to this segment. So AKA, in other words, you're looking for perpendicular lines from the chord to the center. Super important, perpendicular segment to the chord from the center. And here's your implied statement. So get familiar with that, memorizing. All right, so let's use our new theorem on this example 4, using congruent chords to find a circle's radius. So in the diagram, we have QR equal to ST, which is equal to 16. So that means this chord is equal to this chord, both 16. Then we have CU equaling 2x and CV equaling 5x minus 9. Find the length of CU. Well, again, if your chords are equal, then that means they are equidistant from the center. So that makes 2x equal to 5x minus 9. So we set up our equation, solve for x. So we combine the 5x towards the 2x by subtracting, resulting in negative 3x equals, and then bring down your negative 9. Divide both sides by negative 3, resulting in x equals 3. So now that we know the solution for x, substitute it into our expression and double that 3, cu is a length of 6. So let's use the same image but change some numbers with this next example of number 4. So in the figure, suppose that ST is 32 and CU equals CV, which equals 12. So take a minute, pause the video to label everything, and see if you can figure out the length of QR, the length of QU, and the radius. So pause the video here and try these on your own. Alright, you should have gotten a length of QR to be 32, and then the length of QU to be 16. So let's talk a little bit about how to find this radius. Notice on my image that I sketched in a radius, it's in red here, from the center C to end point R. And what this does is create a right triangle. So if I have this length being 16 and this length being 12, this is the hypotenuse of this right triangle that I've created, with the radius being our hypotenuse of the right triangle. So then we're simply doing Pythagorean theorem to solve for r. So plug in all the numbers in the right places of the formula and solve for r. So r should have come out to be 20. So if you made any mistakes or wasn't sure how to figure out your radius, take time, pause the video to make corrections and or fill in your notes. Here we are having a hula hoop party, so more circles to come. Bring your clarifying questions to class tomorrow and see you soon. Have a good night.